Welcome back to our Algebra 2 series and sequences unit lesson 1, sequences home review, part 4. Please make sure you catch parts 1, 2, and 3. And if you find these videos helpful, please give it a like and subscribe to the channel if you have not done so already. So for number 6, we're starting off. For each of the following sequences, determine an algebraic formula that defines the sequence. And so in this case, we're looking for a formula. Now, we're probably looking for what's called explicit definition. It looks a lot like a function in this case. I'm going to be using the notation of a sub n. But you can use f of n if you want to. It'd be the same thing, t of n. So it's because in class we use a sub n for our notation now. Although, again, I've used t sub n for other classes too, but that's okay. The key thing is to figure out how they're changing from one term to another and see if we can come up with some way of describing it. So we take a look at the first one, 5, 10, 15, 20. And we are noticing in this case that we are really adding 5 each time. All right, so this is very similar to what we call a linear function. It really looks like a linear function. So I would treat it this way, almost like in this case, use your first term, here's your second term, your third term, and your fourth term. That would mean I could use the coordinate, kind of the coordinates, where the number term is going to be the x value, and the actual term is the y value. So 1, 5, 2, 10, 3, 15, and 4, 20. And we notice in this case, as the x value goes up by 1, the y value goes up by 5. This is very similar, like I said, very similar to a linear function. And so if it's a linear function, we'll use our slope formula, which says in this case, our slope is equal to 10 minus 5 over 2 minus 1. Now, if I were to do the same thing for these 2 points here, between 210 and 315, from here and then here, we would still get, in this case, 15. We get 15 minus 10 over 3 minus 2. And if I continued with in this case, using the coordinates 3, 4, so, and in this is 3, 15, 4, 20, I would get, again, slope formula, 20 minus 15 over 4 minus 1. And each and every time, I would get a slope of 5 over 1. So again, this idea, if we're increasing by the same number every single time, it's most like a linear function. Okay? And because we're going up by 1 every single time, is what the y value increases by 1. Now, like any linear function we learned before, that once we find the slope, we'll use a coordinate to find the y-intercept. And so we use y equals mx plus b. We use coordinate 1, 5, so we'll say 5 is equal to 5 times 1 plus b. And we see 5 equals 5 plus b. That means our y-intercept is 0. Therefore, our equation we use would be y equals 5x. Now, how do I want to write this as a function, or in this case, the rule? Well, let me just shrink a lot of this stuff here because I want to make sure that I have some space. Oops, make sure I have this here, right setting. Okay, oops, nope, I don't want to do that. There we go. All right, group this together, and I'll shrink all this. There you go. Hopefully it's still visible, ladies and gentlemen. Okay. Although this kind of green line here should be underneath the 1, 5. So notation-wise, since I said we're using a sub n, I would say a sub n is equal to 5n. Meaning, for the first term, I do get 5 times 1. For the second term, I get 5 times 2, and so on and so forth. So this would be the answer for A. Now for B, we see that here, we're going to be going from 3 to 9, and 9 to 27, and 27 to 81. We'll multiply by 3 every single time. And so we do the same thing. We'll use coordinates 1, 3, 2, 9, 3, 27, and then 4, 81. Well, these are coordinates in this case, and they're not linear because it's not a linear function because 9 minus 3 is 6 over 2 minus 1 is 1. It's not the same as 27 minus 9 over 3 minus 2. Not a linear function. But we notice that we're multiplying by the same number over and over again. This could be an exponential function. I'm just going to, again, try to save some space here. Okay, makes it a little smaller because of space. And so we'll use the form we have in this case. We use y equals, well, we have a times b to the x power. And we'll when we do this, we saw before in previous lessons, we took two coordinates and kind of filled them in there. And so we would have, in this case, 3 is equal to a times b to the first power, and 9 equals a times b to the second power. And we would then divide the two equations, solving system equations now. So we're going to take this here and divide by this one. And let's move this over. Okay, and so we're going to divide the left side and right side. We find in this case that our 9 divided by 3 gives us 3. A's divide out, and we have b squared over b to the first power is going to be b. So our base is 3. We would find the same thing in this case for if we took 2 comma 9 and 3 comma 27. So if we're multiplying each term by the same number to find the next number, it's probably going to be an exponential function. So b is 3. We'll find the a value now. So here the a value, we'll use 1 comma 3. So 3 equals 1 times 3 to the first power. That means, well, a times 3 to the first power, because we are trying to find a. We find a is equal to 1, because you get 3a equals 3. Divide both sides by 3. A equals 1. All right, so our function in this case will end up looking like y is equal to 1 times 3 to the x power, or really 3 to the x. Now, how do we write this in kind of our notation? We're going to use, in this case, a sub n. So a sub n is equal to 3 to the n power. All right, now why is it 3 to the n power? The same way, x will represent the term you're plugging in. A sub n was going to be the actual value of the term we have. Okay, and if we try this out, when n is 1, we have the first term is going to be 3. N is 2, the second term, 3 squared is 9. N equals 3, the third term is going to be 27 because 3 to the third. And n equals 4, 3 to the 4 power is 81. So that's going to be this formula here. All right. Now for C, which of course is its own problem here, because we're going to notice that it's not like we're adding the same thing over and over again, or multiplying the same thing over again. Here we see the changes are increasing by 1 every single time on top, as well on the bottom though. But the difference in this case is that the bottom is 1 more than the top. But we're adding in this case. So let's take a look. For A, when we're adding by the same number, we got something very similar to, like, in this case, A of n was 5 equals 5 times n. All right, so 5 represents the number we're almost like the slope in this case. What is the slope? But it's the number we're adding by over and over again. So if on the first term A is 1, and the second term the top is 2, and the third term is top is 3, that would kind of make the fraction n on top. So when n is 1, the first term n is 1 top. But in the bottom, it's 1 more than that. It's always, the bottom's always 1 more than the bottom than the top. So a denominator has to be represented by a number 1 more than the numerator. Well, which we don't know what it is. It should be n plus 1. And our rule in this case, a sub n equals n plus 1. Now you're saying, wait a minute, hold on a second there. Whoa. First off, we can agree in this case that whatever number on the numerator is going to be for each fraction we have, denominator is always be 1 more. Now, Let's take a look. When n equals 1 for a1, we're going to get 1 over 1 plus 1, or 1/2. When n equals 2, for the second term, a2 will be 2 over 2 plus 1, so we get 2 over 3. When n is equal to 3, we get a3, the third term, equals, again, the numerator is n, so that's 3 over 3 plus 1, and that's 3/4. Okay, and when n equals 4 for the fourth term, a4 is equal to n equals 4 over 4 plus 1, and we get 4/5. So this idea, again, is not a function as much as trying to figure out a linear function or exponential function, but this is a different rule giving us each of these terms that we see in this case comparatively. The denominators always be one more than the numerator, and the numerator seems to be just is basically the same exact value as a term. So the first term, numerator is 1, second term, numerator is 2, third term, numerator is 3. Okay, and so this one's a little bit more tricky to find, because when we have to kind of open ourselves up to thinking differently. How, in this case, the relation of the term to the number. So you're really trying to find two sets of numbers. Really, it's like almost two functions. If it was really the set here of 1, 2, 3, 4, that would be, in this case, a of n equals n. And if you had the numbers 2, 3, 4, 5, that would be a of n is equal to n plus 1 for those two. So the two separate linear functions, all right, we can see here, can combine to this one here, to that fraction we want to get, though. Okay, let me make this full page so you guys see everything here. And this was a little complicated, I understand. So if you have more questions, I hope I explained it as well as I can, but if you have more questions, please ask them in the question section below. All right, but this is going to be the end of our homework review part 4 for our Algebra 2 series and sequences unit, lesson 1, sequences homework. So please, if you found this helpful at all, please give it a like and subscribe to the channel if you haven't done so already, and I look forward to seeing you guys in the next video. All right, so definitely make sure to catch up part 5, all right, when we start doing this, I believe, recursively. All right, thanks everybody, take care, be safe.